When we deal with thermodynamics, we're going to deal with many different types of processes, all right? Basically, those that deal with controlling our state variables. And so we have four processes that you need to be familiar with. All these different terms here are new ideas, all right? So the first one that you need to be familiar with is an isobaric process. All right, I want you to be thinking of constant pressure with that. In other words, the change in pressure is equal to 0. The big idea there, okay, to remember, it's isobaric. You got the term right here, baric. Hopefully you watch the weather, and you've heard of something called a barometer, which measures the atmospheric pressure. Okay, so keep it in mind that way. An isochoric or isovolumetric process is one in which the change in volume is 0. Isothermal, one where the change in temperature is 0, and adiabatic is one where there's no transfer of thermal energy. So isothermal is easy to remember for the change in temperature being equal to 0. Isochoric, it's a little bit more difficult to remember, just kind of straight memorization for that one. And adiabatic, okay, each time you have iso in front of it, it's saying that we have the same state variable, but this adiabatic idea, this is just telling us we have a perfectly insulated system and that there's no heat transfer, all right? And there's images here of all the four of those processes as they deal with our piston and cylinder assembly, okay? The isobaric process, constant pressure, the idea there is that you have a weight on top of a piston and that weight is always the same, atmospheric pressure is always the same that's acting on that piston. Isochoric, rigid structure, so the volume doesn't change. Isothermal, your piston cylinder assembly is in a bath of some sort that manages to introduce or remove heat to maintain the same temperature. And in an adiabatic process, you have a perfectly insulated cylinder piston assembly. All right. So here, for isobaric processes, the way we keep pressure constant, okay, we have the weight of the brick in the piston and the atmospheric pressure doesn't change. So the big question, right, is if we're going to have a change in volume at constant pressure, all right, how is this going to happen? Well, the idea is that if we're having an expansion, okay, I have it written right here that the force that's going to be applied, okay, to the piston is going to be equal to the pressure inside times the area over which it's being applied, okay? So the molecules are going to strike the piston and transfer momentum, okay, and kinetic energy to cause it to move outwards. So we see here that there's heat being added. All right, that's where it gets the energy to do this. So we have heat being added, and it causes the system to do work, okay, as that heat is added. So, as molecules strike, okay, when they transfer momentum, the kinetic energy is lost, okay. So as the kinetic energy is lost, okay, to the piston, gas is losing that kinetic energy, the internal energy decreases, and therefore, since we saw from before, internal energy is directly proportional to temperature, we also have a decrease in temperature. Remember, these two are directly proportional. So how much work are we doing here? Well, since we're going to be applying a force to this piston and moving it up a distance s, that's the displacement there, all right, of the piston. That's the work that we do, force times displacement times cosine of the angle between the two. Here we'll assume that the angle is going to be 0. And I showed you before, remember, pressure is just equal to force divided by area. So the force we're doing is just pressure times the area, right? We can substitute that in for force. And the area times the displacement of the piston is going to be equal to the change in the volume, all right, of our system. So the work that's done is just equal to the pressure, which is constant, times the change in volume. So if we graph this on a pressure versus volume diagram, which is a common type of diagram that we look at in thermodynamics, okay, we see there's no change in pressure, so it's just going to be a horizontal line. And if we have an expansion of a gas, okay, the gas will have done positive work. In other words, the work done by the gas, okay, will be positive. And this makes sense because what we see here is a change from a smaller volume to a larger volume, okay, of the gas. That's because of the work the gas has done. And if you guys are doing calculus right now, we're integrating the pressure function with respect to volume, okay, from the initial volume to the final volume. And if you're finding this integral right here, it's going to be a positive integral, okay? If we go the other way, if we compress the gas, we see negative work is done because work is being done on the gas. In other words, we're going from VI to VF towards the left here, and that integral will be negative. Hopefully you have done something like that in calculus if you're taking it, okay? So again, the work done by a gas is equal to the area under the curve of a pressure volume diagram, all right? So let's take a look at some examples with this. Actually, no, we're going to skip ahead to, let's see here. Oh, no, yeah, so we're going to do a derivation. So the way that we can do this derivation, okay, we have expansion at constant pressure, all right? We look at our ideal gas laws, and since the pressures are the same, we have a combined ideal gas law, which is what this is right here, same amount of gas as well. So we see that what we have is a ratio of the volumes and the temperatures, all right, which gets at Charles' law right there. So again, okay, considering the first law of thermodynamics, so if we have an increase in temperature, we have an increase in internal energy, all right? So if we have an increase in internal energy, okay, that means we have a positive increase there. And when we add heat, okay, in other words, delta Q to the system is positive, okay, that means that we're going to have an expansion. That means that there will be work done by the system in this case, okay? So we have positive work, positive internal energy with an expansion, okay, because we have positive thermal energy and we need more heat added than the work that is done, okay? So that has to do with efficiency, actually, and that you can't get out more than you put in. So, our example here is that we have 1,000 joules of thermal energy causing the gas to increase its thermal energy by 200 joules. Okay, so how much work is done in expanding the gas? You can figure that out there. All right. So what if we have a compression at constant pressure? Well, again, we look at the gas laws. Okay, we have Charles's law set up here. If we have a decrease in volume, we're also going to have a decrease in temperature. All right, so the first law, again, if we have a decrease in temperature, we have a decrease in internal energy, so that means we have negative internal energy. All right, for us to have negative internal energy, okay, that means that the work done by the system is going to have to be, we're going to have a negative work done by the system, okay. The reason for that is that it's compression, okay, but delta Q needs to be larger than that, so that the delta U is still negative, all right. So let me repeat this here, okay? For compression, all right, we need delta U is negative, all right, because we have delta T as being negative, okay? If that's true, okay, delta Q minus W must be negative, all right? Now the problem is with compression, we know work is negative with the compression. Right? So if work is negative, what we have here is delta Q, all right, plus a positive, right, because we're subtracting a negative. So that means delta Q must be negative. In fact, delta Q must be greater than the work done on the gas, okay, and it must be more negative, okay, for us to have delta U and negative, okay, so that delta U is negative, and that's the logic there. You can follow the same logic for the previous example with the expansion. I didn't explain it so well, but delta U must be positive, all right, because the temperature goes up. And if that's the case, and we have an expansion, we know work has been done by the gas. That's going to be positive, okay. And so delta Q must be more than work there for that to work. Again, that also, when you think in terms of efficiency, that's also holds, okay. So that is an isobaric process right there. That is one at constant pressure. This next example we're going to look at is an isochoric process, or an isovolumetric process, right, where the volume does not change. So when we want to consider the work done here, okay, we have P times delta V, and if we have no change in volume, we can't be doing any work, right? There's no displacement that's occurring, all right? So the work done is equal to 0. So what we actually end up seeing, okay, with our first law, all right, and actually let me change this here, that's not correct. It needs to be minus W, okay? That with work being equal to 0, okay, we end up with the change in internal energy is just equal to the change in thermal energy, okay? So if we add heat to the substance, we're going to increase the internal energy and the temperature is going to go up, all right? And if the temperature goes up, the pressure is also going to go up based on our derivation here for our combined gas law, all right? So, if we did an example problem, all right, of an isochoric process, we have 1 mole of an ideal gas, okay? It's going to be heated at constant volume. and we're given the volume there. From an initial to a final pressure, it says determine the initial and final temperatures of the gas. We use our ideal gas equation, PV equals nRT, to solve for the initial temperature. And then you can use the pressure law to solve for the final temperature if you wanted to do it that way. All right. And so the question is, does the internal energy increase or decrease? Well, since delta T is positive, delta U must also be positive, so the internal energy of the gas must increase. And you can just think of that in terms of the kinetic energy of the system is increasing, all right, when this happens. Yeah. So the next part asks to determine the work done by the gas during this process. Again, it's 0 joules. Remember, it's isochoric. There's no change in volume, so you can't do any work. There's no expansion or compression that can happen. So the question is, if the change in internal energy is 1200 joules, determine the amount of thermal energy added to the gas. Again, showed this before with our first law, that the change in internal energy is the same as the heat added for an isochoric process. Now, I know that this all seems, very, very removed from any sort of concrete examples, but these are just the fundamentals that we're building up here of thermodynamics, and that's all we're really going to cover. Maybe if we get some time in class, we'll go over refrigeration cycles, which I think that might be kind of fun, actually. So, all right, so that was for an isochoric process. Let's do another example for the isochoric process here, all right? We want to look at 3 different cases of an ideal gas, okay, undergoing different, and actually, sorry, these are different processes. These are not just isochoric and isobaric, but both combined and then one that's neither. So actually, we have 3 different series of processes here, okay? So let's look at the work done and the change in internal energy for all of them, okay? So if they all start at and end up at the same state, in other words, they both start, all 3 start at PI and VI and end at PF and VF, okay? If we want to compare the change of internal energy for each process, it's going to be the same for all. The reason is that the delta T should be the same for all if the delta P and delta V's are all the same, and for them to all start in the same and end in the same state, the delta U's must be the same for all of them, okay? So the next question then is compare the work done by or on the gas, okay, in each process, and then justify our answer. Well, we got to look at the area under the curve. That's our definition of work, is the work done by a gas is equal to the integral of the pressure with respect to volume. And when we look at each of these curves, okay, we see that the greatest area exists under curve 3, and then curve 2, and then curve 1. So in curve 3, we get the most work done, which is an isobaric followed by an isochoric process. All right. So the next part says, let's compare the thermal energy added to or removed from the system during each process. Okay. So if we have the equation that delta Q equals delta U plus the work done by the system, all right, we can, knowing that delta U stays the same and that the work varies for each case, see that the thermal energy added must be greatest in the case where the work done by the system is the most, okay? So in this case, it follows that it's the same order as the work done by each process. Finally, for part D, if the internal energy increases in each case by 500 joules, we can calculate the work done and thermal energy exchanged in each case. The reason for that, we can calculate the work done in the first case, okay, which is going to be just the area under the curve. And since we have these values, right, we can solve for that. All right, that's going to give us 400 joules. The other situation, all right, that we can do this at is going to be the integral, this case here, to calculate the work. We need a little bit more information. We need the temperature at which this happens. Okay, if the temperature doesn't change, it looks like it might be an isothermal process, actually. Okay, and then we could figure that out there. I'm not going to do that right now. I haven't chosen the temperature there, but really that's pretty easy because all you're doing is just finding the difference in the natural log of the final volume minus the natural log of the initial volume times nRT. Again, calculus stuff. If you like it, go for it, try it out. Substitute a fake value in for the temperature there. All right. And then finally, here we have the work done under the curve. All right, it's going to be 2,000 joules. So, in both situations, for 1 and 3, we can figure out the total thermal energy by adding 500 to each of these, right? Which is what we said the delta U was, and we can get the total thermal energy added. All right, so we got a couple conclusions we can draw here. Okay, first, that the change in internal energy does not depend on the path taken. All right, so we see here. Okay, it doesn't matter which way we go. All right, the change in internal energy, all right, is the same for all of these. All right, so that's what we call path independence. That's a very important thing in thermodynamics. Okay, and being able to describe different variables. So work and thermal energy do depend on the path taken between the initial and final states. And how do we know that? Well, we see here the work definitely depends on which path we're taking because it's the integral that we're going to end up with. And therefore, because the work depends on the path there, we see Q depends on the work, and that's going to affect it as well. Okay? So remember, delta U depends on delta T, okay? And delta Q is going to end up depending on the work and delta U there. All right? So, all right. That's it for the first part here with isochoric and isobaric processes. The next video we'll talk about isothermal and adiabatic processes.